Yes, we can start.
Yeah, so you can hear me, and can you see my shared screen?
Yes.
My entire shared screen. Hang on, let me share the correct. All right. Right. So, sorry to clarify, Gerson, I'm just saying you. Can you see my slides?
Yes. Yes, I can.
Okay, but I can only see you anyway. I'll try. So, hello everyone. My name is Stassa Patsantzis, and I'm a PhD research student at Imperial College London, studying ILP and Meta-Interpretive Learning. So that's vanilla ILP. Today I'm going to present my work with Stephen Muggleton on the discovery of the top program, which is a unique object in hypothesis space that is a correct hypothesis that can be constructed without an expensive combinatorial search and in polynomial time. So the work I'm presenting is part of Meta-Interpretive Learning. Meta-Interpretive Learning is a recent approach to ILP that is characterized by the use of second-order clauses called the meta rules as inductive bias to restrict the hypothesis search space. Meta rules are used widely in machine learning, data mining, and ILP, but Meta-Interpretive Learning is unique in that it uses meta rules for reasoning in a refutation proof of examples by SLD resolution together with first-order background knowledge rather than as templates. Meta-interpretive learning systems are capable of learning recursive hypotheses and performing predicate invention without the limitations of earlier approaches. Meta-interpretive learning systems learn by searching a hypothesis space. Each hypothesis space in the is a set of definite clauses. Sorry, each hypothesis in the hypothesis space is a set of definite clauses. We call the set of constructible clauses the hypothesis language. The hypothesis space is the power set with the hypothesis language, and so the cost of searching the hypothesis space increases at a rate exponential to the size of the hypothesis language. Because of this extreme inefficiency of searching the hypothesis space, the largest programs reported in the meta-interpretive learning literature have no more than 5 clauses, with one 6-clause program reported. So clearly, we would like to avoid a potentially expensive search of the hypothesis space, but what alternative is there to a search? So one alternative is to construct a unique object that is a correct hypothesis, but this is possible only provided that such an object exists and that it is constructible. Well, it turns out that this is the case for meta-interpretive learning. So our paper reports the discovery of a unique object in the meta-interpretive learning hypothesis space, which we call the top program. This top program is the set of clauses in all correct hypotheses. A correct hypothesis entails all of the positive and none of the negative examples, and the set of clauses in all correct hypotheses is itself a correct hypothesis. The top program is the most general correct hypothesis that includes as a subset each other correct hypothesis. Hence its name, because it sits at the top of subsumption lattice between correct hypotheses. Since there exists only one set of clauses in all correct hypotheses, the top program is a unique object. This makes it possible to construct the top program directly without a combinatorial search. To construct the top program, we must construct the set of clauses in correct hypothesis. A correct hypothesis is a set of clauses that entail all of the positive and none of the negative examples, as we saw before, which means that each clause in a correct hypothesis entails at least one positive and exactly 0 negative examples, a property of clauses that we might term clause correctness. The set of clauses with this clause correctness property can be constructed by SLD refutation of positive examples, and so by meta-interpretive learning. We propose a simple top program construction algorithm that is a variant of meta-interpretive learning. Our algorithm works in 2 steps. In the generalization step, each clause in the hypothesis language that entails one or more positive examples is constructed and added to the top program. In the specialization step, each clause in the top program that entails one or more negative examples is removed from the top program. This leaves us with a set of clauses that all exhibit the clause correctness property. In the worst case, the top program is the entire hypothesis language, and so constructing a top program can be done in time polynomial to the cardinality of the hypothesis language. This way, we get an exponential improvement to complexity compared to searching the hypothesis space. We have implemented our proposed top program construction algorithm in Prolog as the basis of a new meta-interpretive learning system named Louise. The name relates to an earlier implementation of meta-interpretive learning named THELMA, an acronym for Theory Learning Machine, by the way. The top program is a union of all correct hypotheses, and so it can include redundant clauses. LUIS reduces the learned top program by application of Gordon-Plotkin's program reduction algorithm that removes logically redundant clauses from the top program. LUIS is capable of predicate invention and multi-predicate learning. It can invent new examples. It can unfold hypotheses to remove invented predicates or fold over specialized hypotheses to introduce recursion. It has some niceties like user-friendly Metagol formats, debugging facilities for learning, and so on and so forth. So the original implementation of meta-interpretive learning is Metagol. Metagol is a search-based system. Sorry, there's a reference missing from this slide, but you can find the reference in the Metagol URL that I give here. So we have compared LUIS and Metagol in 3 experiments designed to highlight the strengths and weaknesses of both algorithms. Our motivation for top program construction and for LUIS is not to replace Metagol, but rather to complement it with an approach that addresses Metagol's weaknesses that mainly have to do with the inefficiency of searching large hypothesis space. We see our work as building up to meta-interpretive learning as a powerful and unified approach to ILP, rather than offering a new system to supplant the old system. So our first experiment, you see the results in the slide, compares the accuracy and running times of LUIS and Metagol in a grid world navigation dataset, which is designed so that the target theory and with it the size of the hypothesis space increases linearly as we sample more examples representing navigation tasks connecting grid world cells. Metagol takes more than a day to learn from more than 6 examples at once, and so it times out in our experiment with a 300-second time limit at the start of the experiment, where we sampled 62 examples, which is 10% of all examples. 300 seconds is 5 minutes, by the way. It takes more than a day to learn, and it times out in the experiment with a 300-second time limit. Yeah. LUIS learns a large hypothesis of more than 2,500 clauses, including recursive clauses, in under 200 seconds from about 600 examples towards the end of the experiment. The results of this experiment demonstrate the significant improvement in efficiency that comes from constructing a unique top program or any unique correct hypothesis, rather than conducting an exhaustive combinatorial search of the hypothesis space. Our second experiment compares accuracy and running times on a grammar learning task. The dataset is a simple grammar of the controlled natural language used in the collectible card game Magic the Gathering. The dataset for this experiment is set up so that the hypothesis space includes a single correct hypothesis that coincides with the top program. It's like the entire hypothesis space is collapsed into a single hypothesis, which is the same as the top program. Both systems perform equally well in this case, and Metagol even has a small advantage in training times, thanks to its optimal depth first search with iterative deepening strategy. Interestingly, Metagol successfully and efficiently learns a target theory of 36 clauses, which is 7 times larger than most programs previously reported in the meta-interpretive learning literature. When a hypothesis space includes a single correct hypothesis, Metagol essentially performs the program construction as a special case of its search-based learning procedure. This experiment also underlines the benefits of avoiding an expensive search of a large hypothesis space and constructing a unique object instead. Our third experiment compares the performance of LUIS and Metagol in a dataset with noise in the form of mislabeled examples. The target is a connectedness relation on a two-colored graph, which is an abstraction of more common family relation datasets. We generate data with mislabeled positive or negative examples, or both, or neither. In the slide, the false positives are mislabeled negative examples, false negatives are mislabeled positive examples, ambiguities are both together, and no noise is the obvious, no noise. Our dataset also includes some irrelevant background knowledge that complicates the learning task and makes the hypothesis space larger. When data includes noisy examples, the hypothesis space does not include the correct hypothesis. Metagol is designed to learn only correct hypotheses and fail otherwise, so in this experiment, its accuracy is always the accuracy of the empty hypothesis that only covers the negative examples. LUIS is not trying to construct a hypothesis, but only clauses with this correctness property, and so it returns an approximately correct hypothesis. The worst case for Metagol is on mislabeled positive examples, the false negatives. So this is the upper right corner of the image here. Because with false negatives, Metagol is forced to continuously backtrack until it exhausts its training time limit. This is particularly bad given the large size of the hypothesis space because of the irrelevant background knowledge. The relevant background knowledge also hurts LUIS's performance in the no-noise dataset because it forces it to overgeneralize. We repeat the experiment without relevant background knowledge, and find that this time Metagol fails faster and its training times are improved because the hypothesis space is now smaller, and Luis's predictive accuracy on the no-noise dataset also improves. This experiment also shows us that the benefits of avoiding an expensive search when the hypothesis space does not include the correct hypothesis, particularly when the hypothesis space is large. The experiment also shows us that the top-program construction algorithm has a built-in noise tolerance that complements Metagol with an important ability for learning in real-world domains. Finally, the experiment demonstrates Luis's sensitivity to relevant background knowledge. As a conclusion, the top program is a unique object in the hypothesis space that can be constructed directly, avoiding an expensive combinatorial search. We propose a simple top program construction algorithm that runs in polynomial time. We implement this algorithm in a new meta-interpretive learning system called REES, and we conduct experiments that show that the algorithm is best when the hypothesis space is large, or the hypothesis space does not include the correct hypothesis. In upcoming work, we use the TPC algorithm to learn meta rules from data, and in future work, we combine TPC and Metagol in one system with the strengths of both. Thank you for listening.